And so today the plan is to talk about PFC physics, which is my view of the sort of essential things you should understand if you're going to be using PFC. We're not going to talk about granular flow. And then we're going to essentially spend time just building simple PFC models. And what we'll do is you'll watch me and we'll build these things together slowly. And in the process, we'll be learning about different capabilities of PFC. More importantly, you'll be learning about how one should really be thinking about working with PFC and building up scripts and things in a coherent way. And so those are the kind of things you don't learn if you just say, oh, let's just see a slide set about the graphical user interface, right? So that's what we're going to do. Down the road here, these are quite short things here where we talk about some of the fundamental underlying capabilities that we use to do PFC models, but we're going to see those in the tutorial. And then I'm going to talk about Fish, which is an embedded language in PFC, and all of you are using PFC in a sophisticated fashion. And so you're going to be doing extensive use of Fish. So we're going to have a lecture and some examples about Fish, which then will lead us to talking about bonded particle modeling. And really, the overall main reason I'm doing this set of lectures is to get me to go through my old lectures and make them better, but to try to actually come up with a nice, clean, current, up-to-date description of bonded particle modeling. And so that's my challenge in the coming few weeks as we go through this, okay? I want you guys to ask me questions. I know it's awkward because we're not in the same room and I'm not seeing you. So if you look up in a puzzled way, I can't say, wait, what don't you understand? Most of you know me relatively well. I will not mind getting interrupted. I welcome that. That's how you learn. If you don't understand something, it's very likely that there's other people who also don't understand that thing. So jump in and interrupt me along the way if something is not clear. Okay, let's do a test. Is everybody there? Can you say yeah?
Yeah, of course.
All right, good.
Yes.
Okay, let's go into the PFC physics here. And we'll take a break at a halfway point. Okay, just a second. We're going to go through all this. We're going to pass through all the things we've talked about up to this point. Here we go. Let's do this relatively quick. There's a few slides to catch up here. This is the essence of it. Here we go. All that other stuff is introduction. What's PFC? In 5 bullet points. It has particles. They're rigid. They never deform. Rigid means their shape does not change. There's 3 types of particles: balls, which are either disks or spheres; clumps, which are collections of spheres or disks that do not move relative to each other. So it's like a clump of things. And rigid blocks, which are general polyhedra. And so we have particles, and they can move around. And they're going to satisfy Newton's law of motion. They're going to move around like real system. And when they begin to touch, we're going to create contacts. And here we show the simple example. These are 3 walls. Think of it as a box. This is a wall that's pushing down. There's 3 particles that are yellow. And now you can see the locations where they're touching. Those are red circles. Those are called contacts. And you also are seeing here the forces flowing through the system. This green is the force at the contact. The thickness of these lines is related to the magnitude of the force. And so you're seeing how this is being pushed on the top, but then it's pushing on the side. That makes this guy be in equilibrium. It's pushing those guys out, right? We are enforcing Newton's law, and we're doing it, which is the differential equation, but we're doing it using an explicit finite difference scheme, and we'll go through the basic equations for that. And doing this is what makes it become the distinct element method. There are many different ways that you could make a program that allowed particles to move around. And that whole class of programs is called discrete elements. If you use this type of procedure to solve the equations, it's called distinct element. And this was the original approach of how this entire procedure was developed years ago in the mid-1970s by Peter Kundal. And this is the dynamic simulation, meaning that we're slowly moving forward in time. So there's a time stepping thing. And the other thing that you're going to see here is that this time step is going to, as you're running a simulation, this time step is going to be changing. And it's going to be changing as the stiffness changes in the system and as the mass. It's related to the mass and stiffness, and we'll talk more about that later. The key thing, though, is you're running it, and it's changing a little bit as you're loading the system. So if you want to take a wall like this guy up here and make it move 2 millimeters, you cannot just say, oh, the current time step is this, and I'm just going to apply this much velocity for 1,000 steps, because time step will typically change. And then because it's a dynamic simulation, things are bouncing around. If we take particles and let gravity push them into a box, they're going to bounce around. And so in order to dissipate that kinetic energy, we have a numerical scheme that we call damping for removing the kinetic energy. So if you take a particle like a tennis ball and you let it bounce on the ground, it doesn't come up to the same height. There's dissipation, and we're going to be doing that in PFC as well. Okay. Big picture. We're done. Everybody get it? Make sense?
Yeah.
All right. Thanks. You're that person, Yoon King, who was like me. You're the one who's always like looking in the front. You probably sit in the front of the class and you're jumping in and saying, yes, thank you. Very simple model, particles, contacts. There you see the particles on the left. Here you see the contacts on the right. So the particles interact at these contacts, and what's the thing at the contact? At the contact, there's a force, and that force you can see up here, it's acting equal and opposite. So the red guy is pushing, so this orange particle is being loaded by that red force. And meanwhile, this blue particle is being loaded by this blue force. And these are equal and opposite. Okay. And every contact always has forces equal and opposite that are acting. In addition, they may have micro moments, which you see here. And the question is, how do you get a micro moment there? That seems kind of weird. And it has to do with this. How do we get a moment? The key thing is that you have to now associate some kind of area with this. And that's because you need to resist a bending moment. And so let's take a look at this thing. So think of it this way. We have a current state of the system. There's no moment. And now we're going to move. There's going to be motion. So there's going to be relative motion of the two sides of those things that are touching. And then we have to update this moment. Okay, so let's take a look at what we mean. This is really the way you now need to think about those two particles. Notice I've got this red thing here and this green thing here. These particles now are thought of as having a area, a finite area. In this case, it's denoted by D. Okay, so this red thing here is effectively rigidly connected to the red particle. So this is the surface, the local surface of the red particle. And similarly for the green. And so now, if we take just the top one and you apply a rotation, right? Well, what's going to happen? These guys are going to overlap. This guy's not going to touch. So you're going to build up forces here. And you're going to build up tension here if it's bonded. And so it'll do this. This is the force acting on the red particle. So notice if I rotate it this way, this goes in compression, but this is going to go into tension if there's some bonding there for it to resist this. Notice this is a moment arm. And so if you take F times D, that's the bending moment that's acting. You could like, these two forces acting out here are equivalent to a micro moment acting at that point contact. And that's how moments can occur. And we're going to get these because we're going to have all sorts of bonding concepts. And when you bond something, you have to have a finite size hunk of area that you're bonding. You're gluing it together. Okay. Or does that make sense?
Yeah.
Questions? Okay. And this is the whole thing,
Okay.
forces and moments. Okay. And notice these moments are acting at the contact point, right? So the result of these forces, which are not are acting across the whole thing, you get the result of that, which is a moment, which is mechanically equivalent. So that's why we can do everything at the contact. As long as we allow a moment as well as a force, now we have the complete general concept. If you have two surfaces interacting, there's always some complicated traction distribution across that. And if you integrate that traction distribution, you come up with a moment. Okay. All right. This is pointing out that the 3D model is spheres, the 2D model is disks of unit thickness. And there's an example of a physical system of rods that are stacked together. And so that 2D model is really behaving like a bunch of rods. Okay. And this is actually very important because there's all these papers people write and they build these 2D models and they do a unconfined compressive strength test and you see these fractures forming and it splitting apart and it looks like a cylinder of rock, but actually it's not. It's a collection of these things that are glued together. It turns out though that quantitatively these disks behave very much like the spheres as well. Okay. What are we talking about here? Soft contacts, particles overlap. There's two tennis balls. Let's say that we took those particles now. We're going to model that system. So here they are. They're just touching. They're not overlapping. Here's a wall and here's a wall. And I'm going to stand on top and apply a force. And what's going to happen? This wall is going to move down. And these particles, these tennis balls, this is not a PFC model. This is a real system of tennis balls, are going to squeeze into this shape. And notice how they expand. See, they're wider. And also they form these flat disc-shaped surfaces of where they're in compression, where they're touching. Okay. So this is the real system. In the discrete element model, we don't allow things to deform. The particles can't change their shape. So what ends up happening is they still push down by delta, but there's an overlap that develops at every contact. And that's what you're seeing here. So if I go backwards, you look at the real system, you look at the particles. Okay. In the real system, there's no overlap. But in the model there is. Okay. And that's why we call this a soft contact, because it's allowing overlap to occur. And so all of the deformation, what's the deformation? Delta is the macroscopic applied deformation. Some of that is this. So if you take this overlap plus that overlap plus that overlap, that's going to be the delta. It's all going to happen at those contacts, and these guys won't change shape. Okay. And so that would be a good model of something like a dry, like quartz sand here. That's a dry quartz sand, right? When you squeeze this assembly, the individual quartz grains deform very, very minor amount because they have such a high stiffness. But there's all kinds of rearrangement and there's all kinds of localized deformation at the joints between them, at those interfaces. And so this model, as long as this overlap is less than maybe 5% of the radius, this is a quite good model of this system. On the other extreme, if you had marshmallows and you wanted to model this is not a good model for that, because when you load a collection of marshmallows, much deformation occurs in changing the shape of the marshmallow, right? So we are typically, at least you guys, are going to be using this for geotechnical type applications, and so this is a pretty good model for those systems. It says people. What's going on here? Did someone just come in here? I heard a beep. Okay, let's not worry about it. Let's go back.
Oh, well, I think Shihang is outline. And
Oh, got it. Okay. He actually
yeah.
has to run home because his building is going to get locked, and he'll get locked in his office all night long. And I know he loves me to be a lecturer, but he doesn't want to stay there all night long and have to do that.
Maybe
So
I thought that he's applying to join.
Oh, wait, he's coming back.
Yeah.
Okay, yeah, if you just admit him.
Did someone admit him? Is he good? There, admit.
Oh, yeah.
Shihang, have we recovered you?
Thank you.
Fantastic. I thought you were running home to because you're going to get trapped in your office all night long, but that's not the case.
I'm running the dormitory. Yeah.
Okay, let's keep going here. Now, up to this point, we haven't talked about how those forces are going to be transferred in the system. All we talked about at this stage is there's overlap. So we have to relate that overlap to a force. And the way we're going to do that is have a concept of a spring. And the general concept of a spring means that we have a stiffness, typically denoted by K. And so notice in this system, there's 3 contacts, and so there's 3 different springs. Okay. And what's going to happen to those springs? How is the force going to be related to the deformation? And so in this case, here we go. Here's a particle. It's initially dotted. It's just sitting on this surface, and we're forcing it down by delta, which means a force starts pushing against it. Here we go. This is to the right is opening. That's a gap. And this to the left is overlap. So as we force it to overlap, the force gets bigger and bigger with a slope of K. Okay, and it'll go on forever. That's why there's 2 things here. It'll keep going this way. If I start moving it apart, it'll trace this curve back and forth. Okay, but if I start to form a gap, there's no stickiness, there's no force, there's no tensile force. It won't allow that, right? So this would be like a dry sand. Okay. This is just a quick thing. We talked about this a lot more in the first 2 lectures. I'm going over this again, Yung King, obviously, and Shihang, because I think this is important stuff. If you actually push together 2 elastic surfaces, there's a theory of elasticity solution done by Hertz in the 1880s. And what you really will find is that, notice that as you push them together, this slope will get bigger and bigger. It will stiffen. And so this is, we also have this in PFC. We call this a Hertzian contact model. Most people doing bonded particle modeling just use the simpler linear spring model. Often people who are doing granular flow, like a big giant silo filled with grain and you want to see it flow out, they often use Hertzian models. And that's all I'm going to say about the Hertzian models. But just to say, so in other words, this is pretty interesting. If you actually did this with 2 tennis balls, you should do this when you get a chance. Push them together and you will notice very much that the stiffness gets harder and harder to press them. They do get stiffer, and this is because these are elastic bodies pushing together, and so they will do this. Okay. Good enough? Makes sense so far?
Yeah.
Okay. Okay. And here we go. This is the distinct element method. This is one time step. One time around the loop is one time step. So what have you got? Let's start over here. You go to each particle and it has contacts, which means it has forces and potentially micro moments, and that's the only thing it knows about. So we have to sum up the forces and the moments. We come up with the total force, and we say that's equal to forces mass times acceleration, so we can figure out the change of velocity. And so we can move all the particles. So here's what I'm saying. Update the particle positions, and when we move the particles, there may be new contacts that form, and there may be old contacts that disappear because they're not touching anymore. So we do that, and then we have to update the forces that are acting at those contacts. And again, we look at the relative motion, and that allows us to update the force and moment. So that's here. Contact forces change. Ooh, now we're done. Now we do the same thing. And there is a certain time step, which we'll talk about in a little bit, that can't be too big for this to work. Okay. We're not going to talk about all this cool stuff about Newton and Hooke. The key thing is, look at this equation. The law of motion is F equals ma, and this is boldface because this is a vector equation, right? Force equals mass times acceleration. This is the basic idea of how you update forces. Relative motion, delta, stiffness. Stiffness times delta gives you the force, okay? These two equations are attributed to these guys, Isaac Newton and Robert Hooke. And we're not going to talk about this stuff about Newton or Hooke. You can look at the other lecture. You can read this stuff. So here we go. F equals ma. Let's go and do this one by hand. And let's see if I can do this now. If I can remember how to do this, I'm going to say stop sharing. I'm going to go to my other machine. Okay. How do I make a new? I'm not used to the iPad. Oh, I see. Okay, just a second. Sorry about this. Ah, got it. Okay, now I'm going to try to share my screen on this side. That's not it. Okay, just a second. Help me. Where is the share screen? That's not the share screen. If anyone knows how to share the screen, I've done this before. Oh, there it is. Share the screen. Share the screen without audio. Start broadcast. Okay. Now, oh, good. You can see my screen because I can see it. Okay. Now let's go back so I can write. Come on. Make this bigger. Get rid of this keyboard. I don't want you. How do I get rid?
Just the keyboard button.
Help me.
At the keyboard button at the corner down to the right. Just click on that.
To the right. Oh.
Okay, yeah.
Thank you. Fantastic. Okay. And I don't know. Oh, look, I can even get rid of that. Okay. Here we go. Here we go. So let's just work through this here. This is important, and I have to turn my pencil on. Okay, here's a general packing. Here's my particle, right? And there's another particle, and it's inside of a whole collection of particles. So let's just say here, and the shape doesn't matter. So we have contacts, 1, 2, 3, right? And so if we just look at that particle, that guy, all that guy knows about is this. Let's call this F1 from that contact. Let's call this F2 from that contact. And here we go, F3. So this guy is loaded with those 3 forces. And we can say F equals MA. I'm putting a little squiggle underneath each thing to designate that it's a vector. And F is F1 plus F2 plus F3, right? And so let's go over here again. F equals MA, and we can now write that, and it's a differential equation because acceleration, mass times now change in velocity over change in time, right? Which then we can approximate as a finite difference thing, which is going to be mass times the velocity. Now we introduce a concept of a delta t for time. It's the new velocity minus the old velocity over delta t, right? Change in velocity, change in time. With me? And now we can just rearrange terms. Let's bring them m to this side. So I can say force over mass. Force over, yeah, bring m to that side, multiply by delta t. And now that I've got v at t plus delta t minus v at t, right? And so we're just gonna now look at, we've got all the ingredients. This is the guy we're trying to get, right? So we can just solve for that guy, right? Just rearrange terms. This is the new velocity. It's equal to the old velocity plus, here's the key thing, force over mass times delta t. We know this at the beginning of the time step. We know the total force, we know the mass, and we know a delta t. Somehow we figure out what delta t is for each time step, okay? And so literally that's all we're doing, okay? So as long as we're tracking velocities and we're tracking contact forces and masses, we can update the velocities of every particle. And then we need to update the position. So we do the same thing. This is the differential change of x over change in t, right? Which again is approximately equal to the new x at t plus delta t minus the old x over what?
Over delta t.
Delta t, right?
Yeah.
And so again, we have everything. We can end up then rearranging the terms. The new x at t plus delta t is equal to the old x at t plus the velocity times delta t. And we got the velocity from from before, and now we take that, hit it with delta t, and now everybody gets a new position. Okay. This is the basic idea. We also, because we have a general system with 6 degrees of freedom, we not only have forces, but we also remember there could be a resultant moment here, right? So the total moment on that thing is r cross fi, where r is the radius of the particle. So I'm also can get a resultant moment. And the Newton law for rigid body dynamics is the total resultant moment equals I times omega dot. This is the time rate of change. This is the time rate of change of the rotational velocity. And this is the moment of inertia of the general rigid body. And so we do the same thing with this set of equations because we have to update both the position, we update both the translational velocity and the rotational velocity. Okay. And the last thing to be said here is about this is that this exact set of equations is a little bit simplified. What PFC is actually using is called a Verlet integration, and it's essentially the same sort of thing, except now instead of going like at t and t plus delta t, you can say, look at what's at t, what's at t plus delta t, and what's at t minus delta t, and you can mix all these guys together, and it's a little bit better of an integration. Okay, but that's the basic idea. Does that make sense? Are we good here?
Yeah.
Okay, let's stop sharing. How do I stop sharing? Help me. Stop. There it is. Stop presenting. Okay, are we back to the slide? Not yet. Now I have to start presenting. Here. Boom. Okay, we good? Can you see my screen again?
Yep.
Okay, just point out a couple things here. So here's what we just did. So again, PFC uses this Verlet integration. And of course, nowadays, it's freaking amazing. You just go to Wikipedia and you've got the whole history of Verlet integration. Okay, so that's what it's actually using. And again, everything here assumes we know what delta t is. And we're going to end up, because these equations are approximations, there's going to be a limit to how big we can ever make delta t, right? Just think of it. You got particles moving around and they're bouncing around, going all over. You can't suddenly just take one time step and solve for the system, 10 minutes later, because it has to trace all those motions, right? So I'm pointing that out. Also in this slide set, there's these two magic links here. So one of them is, just a second, these note sets. So back in 2003, I was a professor for a year and a half at University of Toronto, and I gave a course called Microstructural Modeling of Discrete Systems, and it was largely, a lot of it was about the stuff about PFC. And so in that process, I have a whole set of, I call them note sets. These are like little handwritten things where I go through various things that are relevant to PFC. And so in this presentation throughout here where it's appropriate, that one was talking about the law of motion. See, here you go. Force equals mass times acceleration, rotational motion, moment equals I times omega dot, right? So all this stuff is worked out. The details of that are worked out here if you want to know more. And this one is talking, what is this one talking about? Here's this integration business. Here's the finite difference expression. So it's working out, deriving the finite difference expression. Okay. So, and I've given you these things. I'll keep giving you these slide sets, right? So you can go through if you're interested and look at more detail. Okay. Okay, so that's law of motion right there. How do we do this? Get the resultant force and moment, update all the positions. Figure out if new contacts have formed. Now, how do we update the forces? We use Hooke's law, F equals K delta, right? So what's this one going to look like here? Just a moment. This is the useful one. Let's see. I'm going to share this screen again. And do I have to stop sharing? I think I do. Okay, you tell me when you can see the other screen. Come on. Da-da-da. Oh, looking good. Okay. Now, check this one out. This is probably the most important little thing I'm going to talk about. If there's nothing else you learn about PFC, this little thing I'm going to talk about is what you need to understand. This is what makes it so powerful and so simple. So I'm going to go up here. Okay. So F equals K times delta. How are we going to update the forces? Again, let's go over here. Here's a particle. Again, here's the guys that are pushing against it. They're at the contacts, right? So there's my contacts, 1, 2, 3, same guys before. So let's just look at one contact and figure out how to update the force right there. Because if we can figure it out for this one contact, we can figure it out for each of them, okay? So if we now look at that particle, as far as that particle is concerned, all that it knows is that there's a force pushing against it, okay? Now what we're going to do is decompose that force. Here's a straight line. It's going to be equal to a shear component, and it's going to be equal to a normal component. And I'm going to designate this by F sub S and F sub N. Okay, are you with me?
Yeah.
Okay, and so the game here is, given a relative motion, how do we update F sub N and how do we update F sub S? Okay, and I'm going to say there's going to be 3 parameters I'm going to need. So it's a model, it has parameters. There's going to just be 3 parameters. There's going to be a normal stiffness, a shear stiffness, and a friction coefficient. Okay. And so let's look at how we get Fn. So let's do this. So here we go, Fn. And this going upwards is compression, right? And this is going to be overlap. So what does that mean? Let's say there's a wall here, there's a particle, right? We force it to move down by delta n. That's just like you can decompose, let's draw this. There's this guy, and there's this guy. And right there, there's a motion, delta. But you can decompose it into delta n and delta s. Are you with me?
Yeah.
Okay, and it's going to be the delta n that's going to affect Fn, and it's going to be the delta s that's going to affect Fs. So for the delta n, I forced this guy to move down, which means that guy feels now Fn pushing against them. And notice there's no more vector equations anymore. These are simple direct equations. These are scalars. And so normal versus, so if I go this way, this is overlap, and this is gap. Notice I'm measuring delta n going towards the wall. I'm calling that positive. So if I go upwards, the force is 0, just goes back and forth at 0. If I start to go this way, it's going to go up, and the slope is going to be Kn. And the more that I'm applying delta n, the force is growing. If I go the other way, the force comes back. And if I keep going the other way, it just comes back and it does this. And it just keeps on moving around in this space. And it's totally determined by normal stiffness. Okay?
Okay.
Now, The shear stiffness, it's probably going to deal with both of these because we only got two left and there's only one more thing we're trying to figure out. So let's draw my picture again. Here's that system. Here's the initial particle. And we're going to force it to move delta S. So that's the relative shear motion. And what's going to happen at the bottom, it's going to feel a force Fs, right? Because I'm
Yep.
pushing it to the right, it's going to feel a force from the wall pushing it back. Okay? With me?
Yep.
And if I move it the other way, it's going to feel a force going that way, Fs. It doesn't care, right? If it's a 0 point, if I move to the right, it builds up Fs. If I move to the left, it builds up Fs in a different direction. So when we describe this thing, we're going to make this be absolute value of Fs, and this be 0, okay? Okay, you with me? So we're going to say,
Okay.
how then is the F? So it's going to be related to, again, the only thing is delta S, okay? And so again, then, it's going to go up, but now it's going to have a different stiffness, Ks, right? So again, delta S is being applied. I'm making it move to the right. So as I make it move to the right, the force is going bigger and bigger. But it's not going to go bigger forever. There's going to be a limiting force. And let's call this, this value here is going to be friction coefficient times the current normal force. We call this Coulomb sliding. So the normal force, right, there is going to be a normal force potentially acting on this. And that's actually, if you look carefully, I drew this, there's overlap here. So if I draw the whole system, it actually has Fn acting, and now I'm making it move, so Fs is building up. Okay, so this is giving us the sliding limit. And so if I keep moving it in the shear direction, it reaches this limit, and now it just stays there, no matter how much I do it. Now it's just sliding, okay? Then, at this point, what if I now move it backwards? If I move it backwards, it's going to elastically unload like this. And this has the, sorry. This has the same slope as the other one, okay? So I move it to the right, it goes up, starts sliding, I move it back, it unloads. If I now move it to the right again, it goes back up, and it keeps going like this. And it just happily keeps doing all of this, okay? Does this make sense?
Yes, I do have a question. So
Yes.
when we load and unload, we said there it will not be as the normal when it's load and unload in the same place. So for example, if I load and then I load again, I do not expect the same unloading curve, right? There will be different unloading curves
I'm
or
not
lines.
following. What do you mean if you load and unload again?
So
Say again.
for the shear,
Yes.
for example, here we load it and then we reach to the limit and we unload, right? So
Well,
there is two
hold
lines.
on. Yes, so you mean, so when you say load, let's be
Mhm.
clear, you're actually saying we force it to move by delta S. We force it to move to the right.
Yes.
And therefore
And
the
then
force keeps, yeah, go ahead, okay.
and
Gets to
then
here,
we reach the limit, right?
yes.
And we continue until we unload. That's how we get the second
So yes, so
line.
we keep on moving it even more, and it does
Uh-huh.
this, gets to
Yes.
here. Now, if
Uh-huh.
we kept moving it more, it would just keep on moving. But if we start moving the other way,
Mm-hmm.
it comes down like this,
Okay. Makes sense.
okay?
Yes.
Now, let me show you this. This is how I came to finally understand this. Just a second. I need to stop That's not it. Stop presenting. I want to get my camera going here. Can you see me?
Yes.
Okay, watch this. This is the system. Here's my hand. Here's my load. I'm pushing against it. Okay? Think of this. Watch what happens with your skin. So push. It builds up compressive force. If you go up, 0. That's easy. Now, push your finger into your skin and keep the force the same. Now, notice if I start moving it in a shear direction, my skin is elastic. Okay? But eventually, if I keep moving it, oh, I start sliding. And the force is staying the same. The shear force is staying the same. Okay, so that's what's happening. And so look at it this way. I've got a normal force, and I start, you see the stretching of the skin. It's an elastic thing. It slides. Now if I move it back, that elastic stretch is still there. So then when I come back, it unloads elastically the same way on that same slope. Okay, this is what's happening. And this is, one could argue that this is the simplest possible force displacement interaction that can occur at a contact. There has to be a normal stiffness to resist normal motion, and in almost all systems, including your hand here, the normal stiffness is much greater than the shear stiffness. And this is actually a general thing. In the vast majority of real materials, the normal stiffness is anywhere from 1 to 4 times bigger than the shear stiffness. Okay. And so this describes for us the physics here of a contact. So let's go back to this. Okay. Can you see the, okay, you got my screen again?
Yes.
And so again, going through what we just did, there's our particle, decompose the force into a shear and a normal. And actually this shear force is not floating in space. It's actually acting on the surface of the particle. So that's all this guy knows about. Here's the normal force versus displacement thing. And then here is, that's only the normal direction. What about the shear direction? And again, here's what I was trying to talk about. The model only has 3 parameters, and it has a normal stiffness that you'll feel, and it has a lower shear stiffness, typically. And then again, we walk through this. How do we update Fn? We push it down, we have delta n. It loads up at the slope of Kn. If we move the other way, it can carry no tension, so the force is 0. Over here, right, there's an initial Fn here. There's a little overlap. We force it to move. It loads up at a different slope. And then we have this critical thing. And now it's sliding. And now if I move the other way, it's going like this. Okay. What's happening with the energy in this system? Somebody. What happens? Oh, let's see. Let me draw something here to help you. Here's a line. Okay. The energy that is going into that spring is the area under this curve. Because this is, you're integrating force through displacement. And so it's the area under this curve. So if I load up, I have energy stored. If I load back down, I recover all that energy. But if I go way out to here, the total energy, the work that's been done on the system is this whole area here. And then when I unload, I recover some of the energy, but some of it has been lost. Okay. And that's also noticeable because when I unload back to 0, I have a permanent deformation that's occurred. Okay, somehow I started with 0. I forced my finger to move, and now just think of the finger on the hand. It starts sliding, and now if I unload till it gets to 0, it's got a permanent motion. And so during the sliding, you are dissipating energy. Energy is naturally being consumed in that process. While you're sliding, you're not storing any more energy in the spring. Okay. And so so friction in a system is a source of dissipating energy. Okay. Did you guys follow that?
Yeah.
Okay. Okay. So that's what I want to say about this simple model. And we call this particular model the linear model. Okay. Let's go. And here it is. So linear contact model, we're going to draw it like this. We call these rheological components. We have these little symbols, right? These little squiggly guys are supposed to represent springs. Now, the only thing we talked about here was force that was building up. There was no micro moment. And so that, again, means that think of this as that red guy as a little hunk of the top surface, and the green is a little hunk of the bottom surface. And that thing has gone to 0. Think of this. Here are glass beads cemented with epoxy. If I make the epoxy radius smaller and smaller and smaller, eventually I can't resist moment anymore. And so it would be like taking this epoxy and removing it. And so that's what the linear model is doing. So notice there's a normal spring, and I have this little element in here to mean that a gap is allowed to develop. So if you push the spring, these two guys push, but if you try to pull it, it won't take tension. And meanwhile here, and like this line is welded to the top, this line is welded to the bottom. And so now, and this is a slider. So think of it, you have to push it down for this to come into contact, so that now when I move this, I compress the spring, and eventually I could get this to slide. And so this is the basic thing. Okay, make sense?
Okay. Yeah.
It's a very simple model. It's a very simple model. But it's got the key essence of everything that has to happen when two bodies touch. When two bodies touch, there's going to be a normal and a shear stiffness, and it's going to be different. And there's going to be a concept here, if we want to allow these things to actually move around, not just in a trivial amount of motion, then there's going to have to be, somehow they're going to have to be able to slide. And the simplest sliding concept is a friction coefficient. Okay. And so this simple model ends up producing systems that behave like what you see here. Okay, this is a PFC model of discs, and you can see there's 3 walls. The 2 side walls are representing the sides of a bin, and then this top wall is applying a force to push these things down, and the bin has an opening, a gap. And so what you're seeing here are the force chains. This is, again, every contact, there's an equal and opposite force. So here, for example, it's acting straight up and down. It's pushing onto that top disc. But then notice it's going out to the sides, and it's pushing against the next 2. The thickness is proportional to magnitude. And so what's going on here? The load is flowing. It's being pushed from the top, and then it's flowing into the sides of the bin. And these forces, notice these lines are not perpendicular to the surface. That means there's some shear component resisting. Okay. But meanwhile, here, there's not enough confinement, and so these guys are unloaded. There's no forces, right? And there's less and less. And the other thing you see here is this compressive loop, if you will, this compressive arch, they call it. Okay. This is how granular materials are trying to resist motion. They're trying to form a stable arch. And if you have high enough friction coefficient, you can then get stable arches. They're going to be related to the width of this. They're going to be related to the number of particles across. They're going to be related to the friction coefficient, and they're going to be related to the shape of the particles. Big, weird, elongated strands are going to be more likely to sustain a stable arch than little discs, okay? The other thing I want to point out about this picture is this system macroscopically is under very high compression at the top, but there's still places where some discs are not getting loaded. See this guy? Can you see that guy that I'm circling? Upper right?
Yeah.
Okay, notice the force is arching around this guy. This guy happens to be a little bit too small to be able to touch this chain of 4. So he's just happily sitting there. Right there. There's another one. It's because the load is arching around this little guy here. Okay. This is another characteristic of a system of grains being compressed. Okay. This is photoelastic discs. These are things you can build in the laboratory. This is on the left. And they're photoelastic. And the result of being photoelastic means that when you squeeze them, they get loaded at these point locations. And you actually can see these different colored lines. And these lines correspond with these force chains. Okay. This is a real system. This is really how granular materials behave. They carry load through force chains. Okay. And if you look at this carefully, there's the same thing. This guy here is not carrying any load. Right? This is actually taken from the Kundal and Strack paper. This was the paper where Peter Kundal introduced the distinct element method. And he says, hey, here's this simple new method with this really simple linear contact model. And we're going to compare the force chains that we see in the model with the force chains that we see in the laboratory. And hey, it has all the same characteristics. Okay. People who want to explain the fundamental physics of why are granular materials behaving as they are resort to discussing force chains, because this is the thing that's driving the whole system. This is how the material is carrying the load that's applied to it. And so this is the most important thing. And these force chains are totally, again, related to the shape of the particles, to the friction coefficient, and in a little bit to the stiffnesses, but it's mostly the shape and the friction coefficient that determines this. Okay. Any thoughts? Any questions? Force chains. Okay. And this, of course, in PFC, we look at these all the time. And so this is a PFC3D model of a bunch of spheres in the shape of a cylinder that are being compressed. And these guys are the force chains. The black means compression. And you can see how the load is getting pushed across and it's pushing against the sides, and this whole thing's in equilibrium. And in PFC, you can also color them differently. And so now you have the thickness, just like you had before, where that's magnitude, but you color them by magnitude as well. So we can see there's a big force chain here because it's red. Okay, and so these are the kind of things that people are always looking at in PFC models to gain deeper insight into why the system is behaving as it is. Okay, this is the reason the model makes sense, because it produces these force chains just like real material, and it also is quantitatively producing the same sets of force chains, and that's what controls everything. Okay. And the last quick thing to point out here is when you bond these things together, now you don't really have a granular material anymore. Now you have a material that can sustain tension loading. And those systems are still governed by force chains. Because that's how granular material behaves. And if you're going to say a rock is made up of grains, it's grains pushing against each other. Oh, by the way, there's cementation in there too. Okay, that's like a secondary complication. And so it's the force chains of how the load is carried that also will explain all of the behaviors of bonded particle systems, which will also explain the behaviors of rock. People usually don't think about this in rock mechanics because they don't typically start as thinking of a rock as grains. They think of it more as a big sort of solid thing, and then they think of it in bigger length scales. Oh, here's a hunk of rock. It's got 50 grains inside of it. And I'm just going to get stress and strain. So now I'm going to average everything, and I'm not even going to think about the fact that it's the way that the grains are getting compressed that is really the key that's underlying all the physics of what you get. Okay. Okay, you with me? We good?
Yeah, well, I have a question about the force chain. That how could we describe the force chain in real system? I mean, maybe in the lab.
And what do you mean by describe?
Well, draw it, or because you mentioned that when we use the method to calculate the force chain, it's very likely to the real force chain. But how could we know the real one?
I think part of what you're saying is how can we believe the model to be the same as the real system? And I think another part of what you're asking is there a way to quantify this force chain information in addition to just looking at pictures? Yeah, those are excellent questions. The verification is in the sense of how closely does the model behave like these disks? And like for rigid disks, not rigid, but very stiff disks, the model and the experiments they do photoelastically, people have convinced themselves that there is a very, very good correspondence. You're not going to get exactly the same picture unless you can somehow exactly replicate the positions of every single one of those things and the sizes. And so you will very rarely build a model that's like exactly the same, okay? But what then people do, this is now related to quantifying this, okay? One of the things they do is they say, let's look at the orientation of every one of these forces, okay? Like this force is vertical, right? And this force here is horizontal, right? Mm-hmm. And you can say, if you compress these disks isotropically, the same from horizontal and vertical, in general, if you look at all the distributions of the contact orientations, they will be the same in all directions. But if you compress it this way, vertically, and put very small confinement here, most of the force chains will be going vertically, okay? And so this is one way to begin to quantify. That's like a big crude quantification. What direction are most of the force chains going? Another thing people will often do is they'll look at something called coordination number. And coordination number is the average number of forces acting on a single particle. So this guy has a coordination number of 3. this guy has a coordination number of 4. And so you can compute that in a model. You can also do that on these photoelastic discs. Okay. And again, that will tell you things that are relatable quite well to different characteristics of how a granular material behaves. Okay.
Okay.
Ayat, what other ways do people quantify these?
You talked about orientation, so they do orientation and magnitude. This is what they call the polar plots that we were trying to figure out.
Mhm.
So the orientation and the magnitude is mainly what they are focusing on.
Mhm. Mhm.
Yeah. And probably later on, some of them they were associating that to the orientation of particles as well. That was probably more advanced quantification.
Sure.
Yeah.
Sure. What I can tell you also is I learned so much stuff starting to work with PFC because there's been people who are like physicists who study granular flow. These guys are not engineers like us. These guys are proper physicists. And they do all kinds of analysis on force chains. Again, because that is the fundamental thing. Everything else produces force chains. It's the force chains that control everything. And so they do all kinds of integrating of these quantities to try to come up with different ways of characterizing them. And I don't know all the details. Okay, so does that make sense? Is that
Okay.
helpful?
Yep.
Yeah.
Um,
I do
here's
have
the
a
last
question.
thing. Oh, please go ahead.
You were saying that people in the lab quantified that. Is it possible, or is it like this method, the photoelastic, or they were calculating that by hand, or how?
I don't know. I know that clearly people must do this if you read these photoelastic disc papers. And I don't know for sure about other things.
Okay.
One thing I do know is some years ago there was basically a theoretical person using PFC because she studies, she wants to understand the constitutive behavior of granular systems, the stress strain behavior. And she would do all kinds of work with, let's change the shape of the particles, let's run discrete element things, let's quantify the force chains. And based on doing all sorts of those numerical experiments, she would then develop a constitutive model, which is a stress-strain relationship that people would use. So, yeah, but I don't know too many details. I know there's these physicist guys. They talk about force chains and they use these kind of models, among others, to get them. Okay.
Yeah. I have seen some papers about the photoelastic methods in the one of them is the paper from Ruben Jones in MIT, and his work is mainly about to visualize the force chain and even quantify the force chain. So it's really interesting. You see the video and you see how it propagates light. So I think people do have some skill, some method to quantify the detailed stress. Maybe not that at that a simple, maybe not at that small level, but they did it, I think.
Yeah. Okay.
And yeah.
And the paper you're describing, these are works on real materials that he's looking at these things, and he can somehow quantify force chains in real materials.
Yeah. They use the photoelastic sphere. The
my
paper
God.
is
Okay.
Publicated in the Proceeding of National Americans. Maybe okay. I will give a link or the paper name.
Yeah.
Please.
Okay.
If you could do that, that'd be great. It's a perfect thing I can add to the lectures here as well. Yeah, please do that. Please do that.
I can just question here, maybe.
So Yung King, the other thing you'll see a little later perhaps is like here's an example. Imagine this is a soil, okay? And we have a big building, but it's only 1/3 of the width of this box. And we now push down, okay? What you will see is very high compression bulb here, but then there'll be almost no load out to the sides. And then the compression will slowly dissipate as you go deeper into the soil. And so this again, this is showing, oh, this is how the soil is carrying the load. There's a region of very high compression right near where it's being loaded. And they look at these force chains again to say, oh, that you can sort of see that's where the load is being carried, right?
Okay.
Okay. So force chains. Here is an even more fun set of force chains. So some years ago, I was given these lectures and I did this stuff, talked about force chains, and suddenly this guy like starts going crazy and says, oh my God, there was a game I used to play as a child. And I think it has to do with force chains. And I was like, no way. And so he went and he actually bought this game and sent it to me. Okay, I have this game. It's sitting in my office. It's in my hand, actually. So you can, I think you can see the idea. These are wooden discs. And what you do, and here is a wooden piece of wood, and here's a spring. So it's pushing against it, right? And so what you do is you pull this back, you put these in here, and then you let the spring push them, and now it's static equilibrium. And there's 3 sizes. The color relates to the radius of the disc. And so this is a PFC2D model. This is very well approximated the behavior by a PFC2D model of discs, right? And the game is, it's like I say, okay, it's your turn, Ayat. You must choose one of these, and then you see these little things stick out. So then you take your fingers and you very rapidly pull it out. And if you're lucky, it just readjusts a little bit and you're good. If you're not lucky, the whole thing will blow up, as you see here. Okay, now why is that? It's because your hope, see those guys? There's no load. There's going to be discs in there with no load. So if you pull this one out, nothing happens. But if you pull this one out, there's a huge load being carried. If I remove this, everything has to redistribute the load, and it may not be able to do that in a reasonable way to get a new stable configuration. And so this is a game that demonstrates force chains. Okay.
Okay.
So with that, sorry.
Go.
So with that, we can also say that the force chain is a function of size.
Oh, absolutely. So the force chains are a function of shape. Oh, correct. They're a function of friction coefficient, shape, and size distribution.
Okay.
And so this is showing it's a function of size distribution. If you make all the discs exactly the same size, they will not have this arbitrary packing. They will perfectly align along the walls, and then there'll be another aligned system that like fits in the chinks, and you'll get this crystalline arrangement. That will behave very differently than a heterogeneous arrangement. And so when we build granular systems, you usually, or we're building bonded particle models, if we want it to behave like a sand or a geomaterial, we will give it a size distribution. We will not make them all the same. Okay. And we'll play with this and see this when we start writing some code in a little bit. Okay. Okay, we good? We good? We're about ready to take a break, but I don't remember what the next slide is either. So let's hold our breath and see, and it might be a good time to stop. Oh, last one. Oh yeah, wait, a few more slides. This is important. This is the most important thing, okay? Notice what I'm saying is a linear model, 3 parameters, plus shape and size distribution. Those things that system will behave like real granular material. Okay. And this is a quote from a paper. This was one of my IEP students from a long time, from 2018, Garcia. And Bray is a very famous geotechnical professor at Berkeley. And they wanted to investigate this stuff. Is this DEM thing actually quantitatively behave like granular materials, like soil? And they did all kinds of studies, and they conclude with that very powerful statement right there. Consistent with the principles of critical state soil mechanics. If you don't know what that is, critical state soil mechanics is a very powerful way of, in a stress strain way, characterizing all the different very complex behaviors of soils. And what they did here, they didn't even do the proper shapes. They just used clumps to get a more interlocked system. So they used 4 shapes right here. These are clumps. So these guys never change shape. This never breaks off. And then they gave the real size distribution of these things for a Fontainebleau dry sand. And then they did all sorts of different direct shear tests and things of that sort. And they, make this conclusion. So if you have even the linear model, if you have the shape in there, and so notice the shape, they did not use discs. Discs and spheres will behave very differently than most sands, unless the sand is very, very spherical shaped grains. And most sands and most granular materials are not spherical. And so therefore the shape is, you often need to put in the shape. So here's an example of, now this is a bin flow. These guys want to understand how material flows out of hoppers, for example. And so this is corn. The length scale here is about 1 meter. And this is a laboratory experiment. And there's a plexiglass plate in the front so we can see through it. And these is corn, like corn that you eat. So that's like 5 millimeter grains. And corn is actually not spherical. It's like rice. It's like an elongated thing. And so he then did all kinds of studying, the guy who I'm going to mention here and give his papers and stuff, of these types of systems, and he found that he needed to use clumps. So he has overlapping particles that are similar to the shapes of corn. Okay. And this is a bin flow test. So there's a wall here in reality, and suddenly you open a trap door here and you watch the material flow out, and you're going to do the same thing with PFC. And so we can watch all of the complex granular physics. The pile is forming, it's forming an angle of repose. There's a certain angle here that gets formed, all these different things. Okay. And so again, even with a crude type representation of shape, as long as you have that in there, you're getting quantitatively the behavior of granular materials. Okay. And the last thing I'll say is there's a whole entire lecture about PFC and granular flow, and I'll just let you look at that yourself if you're interested in this topic. That's all we're going to talk about at this point here. We're halfway through, and we're at a good stopping point. And I'm going to suggest we actually take a 15-minute break, because I'm going to jump in the car and get some coffee, and I'll be back in 15 minutes. And you guys should go stretch your legs and things. And I know it's late, except for Ayat, where you guys are. So it's 9:30 a.m. here. We'll resume in 15 minutes at 9:45 my time. Okay?
Okay, no problem.
Okay, good. I'll just keep everything running. Here we go.
Okay, see you later.
So, Dr. Potyondy, what are you growing in your garden?
Ah, can you hear me?
Yes.
Yes. You will see in 1 second. That's what I'm getting those pictures here. Just let me get that here. Let's see. It.
I actually tried to grow a garden this year for the first time in my life as well.
Oh, okay.
Yeah.
Is it working?
It is. I'm getting some tomatoes, so
Excellent. Okay, here I'll show you what I'm growing in my garden. Check this out. Now let me see, share the screen.
oh, nice. Lovely picture.
You see
Wow.
my dog? He's
Yeah.
such a great dog. Look at that dog. Some friends brought those flowers the other night. Okay, garden though. Here it is. So here's the garden. There's cucumbers.
Cucumber.
There's
Nice.
eggplant.
Oh,
There's
I love eggplants.
tomato. And then these are called honeysuckles. And I just like things that grow up on strings. And you can see I've done a lot of fun things with strings. And so if we
Nice.
compare, this is the height a week ago. And you can see here, look at this, how much is, you can see in here, and there's no strings. And now
Yeah.
there's much more, and these things are way up to the top. So
Love it.
that's the garden. Okay. And I managed to get my coffee as well. So I think we're good. Okay. Is everyone here? Ling, are you there?
Yes.
Fantastic. Okay. All right. Here we go. This is another basic thing. This is the contact, right? So contact, think of it as an interface between two things. We're going to call these pieces. When they're touching, it's two surfaces touching. And so again, we're going to talk about pieces. So like if you have a clump, these things are called pebbles. When you push two of them together, a contact forms between the pebbles. Okay. And like if you have a wall, it's made up of three facets. A contact forms between like a ball and a facet. Okay. So it's this idea of pieces. It's the part of the surface where the contact is. Okay. And this is just showing all the different possibilities. Notice there's a clump, but a contact is with this ball and this pebble. This ball or this pebble and this pebble, right? Here, it's a wall, two facets. This pebble and this facet, that's what's happening. Okay. And there's different types of possibilities now because these are the different PFC pieces. And here we go. So you can have a contact between a ball and a rigid block or between a ball and a facet. We'll talk about this later when we do more sophisticated things like loop through the list of contacts if we need to do that for some reason. Maybe we want to quantify the force chains. So we have to go through the list of contacts and grab forces and do things with them. So contact model. There are many contact models in PFC. And what they really are is you should think of them as particle interaction laws. It's how the particles interact. And a contact is always only between two pieces. You can't have 6 of them at a contact. There's always just 2. And again, we're using that soft contact approach. So overlap is happening, input, relative motion, output, update the force and moment. Okay. Here's what's actually happening here. Okay. This is the relative motion. This is the translational velocity, and this is the rotational velocity. This is piece 1. Sorry, this is piece 1. This is piece 2. So If you take the translational velocity of 2 minus 1, that gives you the relative translational velocity. And so that's what we see here. Now, look at this. Here's two particles. These are two cardboard discs, okay? And I take them and push them together and they overlap. This is what's happening in the PFC. They're overlapping. That means we can draw a line from center to center to establish a normal direction, and this is normal to the surface, to the two surfaces. And there's going to be an overlap region, a volume of overlap. And what we're going to do is we're going to choose one point inside there that's going to be called the contact point. And all the action happens at that contact point, okay? And so we can overlap these two cardboard discs, and I can take out my pocket knife and I can plunge the knife through here. And now if I move them apart, you see that I've made a hole in disc 1 and I've made a hole in disc 2. So the contact force is equal and opposite. This guy is going to say, I have a contact force at this location pushing me in that direction. And conversely, I'm over here. And so when I sum up the total force and when I sum up the total moment about my center, it's actually acting here, okay? And so this is how one of the details of how we're handling the overlap. There's always a volume of overlap, and there's always in the center of that is where the contact is. Okay. There's all sorts of built-in contact models. Here's our old friend, the linear model. And this is typically used for granular materials. And then there's all these different guys that have been developed over the years to do bonded particle modeling. And when I lecture about bonded particle modeling, I'm going to actually do it by starting with the simplest possible one historically. And like we had that one and it didn't seem to match this. So then we came up with a different one. And then that matched a few things, but it didn't match something else. And then we came up with another one. And there's there clearly has been like a historical evolution of these things. And so we'll talk about these when we get to the bonded modeling stuff, okay? Oh, and then here is all sorts of models used for granular material. And again, we're not going to talk about the details, okay? And then, just for fun, the concept of a contact does not have to mean overlap. The concept of a contact is interaction between two bodies. Interaction between two bodies. Well, magnetism is an interaction between two bodies where they're not even touching, right? So in PFC, we can do that kind of stuff because we have a contact. So what we can do is we can implement the physics. Here we go, two particles. We're able to create a contact if the particles get within a certain distance of each other. You can actually do this in PFC. You can tell it, I want you to start running so that if two particles are within 3 millimeters of each other, you make a contact. Now, once you have a contact, remember, it's just relative motion, and we have to update the force. And so we can use equations. They don't have to be the linear contact model. They can be the magnetism equations. And so now we have magnetic dipoles. Each of these particles at their center is considered a magnetic dipole. And this is a magnetic field. And here's the magic equation. This is the force between the particles. This is the moment between the particles, right? And so you implement that in the contact model, linear dipole model. And so now watch this. So if you have two of them, behaves just like two little magnetic balls. But you can make it behave like any shaped magnetic thing, because what you can do is you can say, oh, well, now I want to have a square magnet. So I'm going to make a 3 by 3 by 3 collection of balls. And every ball is a dipole, which can have a contact with every other ball. And so each contact does this. But when you take the result of all of them, now it behaves like two square magnets. Okay. That making sense? Basic idea?
Yep.
Now, watch this. So, compass. What do we got? 301. Oh, come on. Let's see. Just a minute. PFC Lectures. That's the only one that's not in the PowerPoint. So you can watch this for fun. This is the kind of stuff. See, you guys are in the wrong field. You should not be engineers. You should be physicists, because all of these physicists do crazy stuff like this and get paid for it. Okay. So if I go to 301, here is an example of this, of a compass. There you go. He's going to rotate the top and the bottom's going to follow. Magic. Late 1700s, early 1800s. That was magic. Physics did not explain magnetism. Here we go. PFC3D compass. This is the magnetic dipole business. The top one is being forced to rotate. The bottom one is following along. And it takes a while. There's a time lag because this has mass until it falls along, right? So there's one. Here's another one. This is real. Watch this. These are two magnetic particles. He's going to let this go. Boom. See that? Here's PFC. Same thing. Boom. Right? It's just magically happening. That's super simple magnetic dipole model. Here's another one. This is one of these crazy things these guys built. That's what these physicists get to do. This is a bunch of pieces that all fit together into a sphere, but each one is a magnet. So this is a PFC model of that same thing. Look at this thing. I think that one is super cool. Watch this thing again. Here we go. Boom. It's like magic. So I show these partly for fun, but partly to illustrate the idea and the power of the discrete element method. Because you can generalize. Peter Kundal came up with the method and he was applying it to simple systems that were like grains of sand. And for those systems, if you just have a Kn and a Ks and a friction coefficient and the shape, you can get really good proper behavior. However, you can generalize the method to just say, let's put some physics of two particles interacting. And so thus, you can do things like magnetism. There's other people who've done carbon nanotube behavior, and I'm not going to talk about that, but with the same idea, with this interaction at a distance. So here we go. Fundamental assumptions here. So these particles are rigid bodies, okay? And they have a mass, okay? They're all moving independently, and they can move in the proper way that real bodies in 3D space move. The motion can always be decomposed into a translational component and a rotational component. These particles only interact at contacts, and contacts are always between two particles. And this is one of the reasons why. It's because here's these rigid blocks, but if you look closely, they have these rounded corners and vertices. And so because of that, when they touch, they can only touch at between two. Okay, you can't squeeze another one in there because they have these rounded surfaces. Okay. So this is useful for us when we start doing sophisticated things with PFC, because we're going to do things like, oh, let's loop through all the contacts and let's find out what's going on there. Well, oh, at every contact, there's only two things. There's something there's a surface on one side and there's a surface on the other side. That's it. This uses a soft contact approach, right? Which means these particles overlap. And the secondary assumption here is that that overlap is relatively small relative to the size of the particle. And we're going to say that that overlap is actually negligible because we're going to have a single point in 3D space where the contact lives. Remember when I had those two cardboard discs. They overlapped, and actually there's a whole volume where they're overlapping. There's crazy complicated stuff going on there, but we're going to say whatever's going on in there all works its way down into a force and a moment at that one point. Okay. This is this idea of the contact model, right? Relative motion, update force and moment. There you go, you're done. And then we have this idea of putting in what I'll call bonds. Okay. And the idea of a bond is it's like cement and you can carry tension now. And the other aspect of a bond is that if it's intact, it's just carrying tension. It's just like a spring, but it can break. And suddenly when it breaks, now it's just like the linear model, Kn, Ks, and friction. Okay. And if you put in bonds also, you can have particles that are not even touching, because you could say there's cement in between there. They're not even touching, but there's a bond. So the bond's going to carry load. Okay. And what people then will often do is they take these simple models and they make a little, they kind of put them together in creative ways, and they can create a cluster of particles. So here's a cluster of particles. Here is real grains of sand that have been digitized with all this crazy scanning technology that people have nowadays. And then based on that scan, they know the centroid of each of these. They took that centroid and made a PFC sphere that had the same volume. So now they have this packed sphere assembly. And then they said, oh, each sphere is made up of smaller spheres that are glued together. That's a cluster. And so now when we load this, the clusters themselves can break. So if you think of the cluster as a grain, the grain can break. Plus, of course, it interacts with the other guys. Okay. And this is an example. This is work from Professor Al-Shibli at University of Tennessee. Here is a single grain of sand. Look at the length scale, 0.7 millimeters. He squeezes, he actually does these experiments. He does them in a synchrotron, and he's able to get this kind of resolution. So this is now, he's built a thing to do these loads of these tiny things. So he can load, basically do an odometer test on, here we go, 3 grains of sand, or a little more than 3. And so of course, then you can resolve the details, how that thing breaks, right? And even something as apparently simple as a grain of sand is a very, very complex thing when you zoom in to its length scale. Like this thing, this looks like an asteroid, or it looks like the surface of the moon, right? It's not a nice, simple thing like we like to think. And so look how it's breaking. Is that a fracture? Well, it's a complicated fracture because it's got intact material in there, right? You know, at a macro level, what's happening is there's a grain getting squeezed between 2 other grains. And if you squeeze something between 2 other things, you tend to split it down the middle like this. So this is an example of doing clusters. Some other work that Al-Shibli's group has done is you can do these clusters for any shapes in PFC. So here's what you saw. These are spheres glued together to represent a grain. These are, you start with the scan of this shape, and then you turn it into a collection of triangular facets, and you turn that into a whole bunch of internal, I believe these are tetrahedra. So it's a tetrahedra mesh inside, and then you say, oh, every tetrahedron is a PFC rigid block. And when you have 2 rigid blocks, because these are tetrahedrons that perfectly fill space and fit together, every rigid block has a facet that's exactly the same on each side. And so then you can say, oh, well, I can put bonding between those facets, and then they can begin to break. And so here you go, you're crushing the bottom piece. These colors are what we call fragments. You start with a rigid block in there, and you find every possible rigid block you can traverse to without, that's still part of the same group of bonded stuff. So it's a fragment, right? And here's the journal paper if you want to see more about this stuff. Okay, that's a little idea, a precursor to bonded particle modeling. We good?
Yep.
Excellent. One additional thing. think about this type of a model, it's crazy complicated. At one sense, it's crazy simple. At another sense, it's complicated. Just think now about the model. The model's running. All the particles are packed. So there's 63 contacts. Great. And every contact has a contact model. For example, the linear model. Now, when you start to squeeze that assembly, you're going to start to form new contacts because guys are going to start touching. Well, the question then is, what are you supposed to do? Because when a contact forms, there's two things that need to happen. A contact forms. PFC needs to decide which contact model. Linear, dipole, parallel bond, I don't know. PFC has to figure out what contact model to put, and every contact model has parameters, what value to assign to all these new guys, okay? And so we have a concept of a table, and we call it a contact model assignment table. How do we assign contact models, okay? And so we basically have, based on the types of contacts, this is a ball-ball contact. This is a ball facet contact. You can tell it, you can say, okay, by default, every time two balls touch, put in the linear model and give it properties of Kn, Ks, and Frick with these values. But then you might say, oh, but when the balls touch the facets, when the balls touch the walls, let's give them the linear model, but now let's give a zero friction. And so you set this up at the beginning of the simulation. And so if we now have a box with particles, like an odometer test, we start to squeeze it, and this system now, every time a particle touches a wall, it'll give it zero friction. But every time a particle touches another particle, it'll give a friction of 0.5. Are you with me?
Yep.
This is the idea. So the simple way to use this is to just say, depending on the type, here's what the values, here's the type of model, and here's what you give it. Or you can even just say the default without a type. And that just means all the time, for any reason, any contact that forms, this is what you do, okay? And you can do much more sophisticated stuff. But the basic idea here is I can say, oh, what about a certain part of the model that's in this range of X from -2 to 2? I want those guys to be stiffer. I want their Kns to be 10 times bigger than the other Kns. And so you can do that. This is basically telling it in the range, in the region between -2 and 2 of the X coordinate, if you are such a thing, now do this, okay? So it's completely general, and it allows you then to handle these complicated cases, which are often what people are doing in these PFC models, okay? Let's not worry about this. You can do even more stuff, okay? Okay, does that make general sense, this contact model assignment table at the high level?
Yeah.
Okay.
Yeah. Well, I have
go
a
ahead.
little one question.
Yes.
We use the CMAT to set up the contact information and the physical properties. And my question is, if we use the CMAT default type of ball like this, and we give the ball properties with different stiffness and friction coefficient, and which property the system would use to calculate the contact and the force is based on the properties of balls or this contact information.
Good question. You can do that, and I can't remember right offhand how to do it. I'll have to tell you later. But you can do that.
Okay.
By default, it's set up here so that you have a contact model which has properties, Kn, Ks, and Frick. You're talking about a system where at the contact, based on properties assigned to the two particles, now you figure out what to use at the contact. And there is a way to do that in PFC. We talk about inheritance. And I'll have
Okay.
to tell you that separate, okay? Okay,
Okay.
good enough for now?
Okay.
Okay.
Mm. Yeah.
Good question. One other thing that you should be aware of is what's happening here under the hood. The simplest possible way to make a discrete element program is to say, I have a particle, so you have a data structure that stores information of the particle. Some of that information is things like radius and mass. Some of that the information is velocity and position. It stores all that, keeps updating that. You need some graphics that can draw that stuff, right? And you need to have some method of finding new contacts when they start to touch. And so the simplest way to do that is to just have a list, let's say 1,000 particles, and you go to particle number 1 and you compare, is it overlapping particle 2, 3, 4? You just go through and compare them all. And then you go to particle 2 and you compare it with everybody else, okay? And if you do it that way with modern computers, after about 20,000 particles, your system is going to run very slow. And that's because you're doing a lot of comparisons that are not necessary if you're clever. Okay. And so what we can do is use what we call a cell space. This is from the world of computer science. Okay. What does this mean? What you do is you create a domain, which is a physical rectangle in 3-dimensional space. And this is in 2D, it's a rectangle. In 3D, it's a bounding box. Certain distance in the X, certain distance in the global Y, certain distance in the global C. PFC then knows that all the action is going to be in that domain. Okay. Now, it uses that to do this cool thing called a quad tree or octree. What does it do? In 2D, it's called a quad tree. What does that mean? Start with now you have particles. Here's the system. You can see there's these little black guys. They happen to be in a group, and there's other guys here. They're just floating around in the domain. The goal is now to do what we call contact detection. How do we figure out if they're overlapping? And just think about it. Every single time step, we need to do the contact detection. Every single time step. Okay, so you take the domain, it's one big rectangle, and you break it into 4. That's the blue. And then you say, are there particles in there? And here, this guy, oh, there's no particles in there. I'm done. I don't need to break this any smaller. Okay. And or you might say, are there just a small number of particles? So if there's, in this case, there's not many particles, so I'm done. And here I'm done. But in this blue guy, I don't know, there's 22 particles. So I have to do another level. I have to take this guy and recursively break into 4. And now this guy, nobody, 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 I'm done. Oh, this guy, break them smaller. Oh, this guy, break them smaller. Now, once you have this established, if I want to say who's in contact with this guy, I only have to search the cells near me, these big cells. I never have to check this guy against these guys because they're far away because I've recursively divided space. And the result is I drastically reduce the number of checks I have to do, and therefore I greatly increase the computational speed. Does this make sense?
Yeah.
And if you're a computer science person, this is freaking totally cool stuff. Look, the black. The black is a node right here. The black gets divided into 4 regions of space by blue. Oh, here we go. Each guy, 1, 2, 3, 4. 3 of them don't go any farther. Oh, one of them does. It breaks into 4. This guy breaks into 4. You end up producing a data structure called a quad tree. And you use this data structure then. The guys at the bottom, this is called a tree. The guys at the bottom are called the leaves of the tree. The leaves of the tree are the final cells, and you basically can figure out very quickly where you are in space if you know the topology of this quad tree. And the same thing applies in 3D, except then you break it up into 8 quadrants. Okay, so this is what's going on in the background. The one result of this is that whenever you build a PFC model, you must at the beginning specify a domain. And you basically make it a little bigger than the region where all the action is going to happen. Okay. Are we good? Make sense?
Yeah.
Okay.
Well, so how could we deal with the particles that are near to the line? How can I say that? 边界 in Chinese.
Boundary.
Do you mean the particles that are near the edge of a cell?
Well, yeah.
Well, for the logic, it doesn't matter. I mean, every particle is going to uniquely get mapped into only one cell, depending on its centroid. And if you know which cell you're in, you can figure out the local set of cells spatially near you. And then that's what you do. Now, you may also be asking, if you define this domain, what happens if for some reason a particle reaches the boundary?
Mm-hmm.
And you can specify that. Typically, what you then do is you either destroy it or you just tell it to stop. And it just sticks there. Usually that's totally okay. It's usually not happening. But like if you build a specimen and one of the guys bounces out, it's just going to bounce out of the specimen and keep going. And you really don't care about that guy. So it just reaches the edge of the domain. It just stops. Okay?
Okay. Okay.
Now, talk a little bit here about time step, critical time step. And for Yongqing and Shihang, we talked about this already, but I'll pretend we haven't because you other guys are here as well, right? So every time we make that loop through the algorithm, we need to have a time step. And it doesn't have to be the same. Every time we start the loop, we need a time step. That's all. And the time step might be different every time through the loop. And the key thing at the top is what we're doing. We have to somehow make sure that we can integrate those equations. That's what we're doing. So, and the key thing is a simple way to think about this is that the PFC model is a manifestation of this physical system. These are tennis balls with springs. I'm going to show you this thing in a second, a video of this. Okay, I wish I had built it. I need to build this actually. This is the kind of stuff physicists do. This is from a physics website. And they're using it to demonstrate, I don't know, some kind of elementary particle or something. But this is basically an atomic lattice. But we don't care. It's tennis balls with springs. And this is what PFC is. Each tennis ball is a mass point. That's a particle. And each spring is a contact. Literally, masses and springs. And when you hit this, it starts vibrating differently everywhere. And just think, one of these guys is vibrating the fastest. And so that means that we have to take a time step that's smaller than the time it takes for this guy to move this way and back. Okay, we have to break that up into a bunch of small steps because there's no way we can trace the motion of this way and back unless we take a bunch of sample points. And so what we have to do in the PFC world is figure out which guy in the system is vibrating the fastest. And then we might take 4 time steps over the period of that guy. Okay, that's the idea. And if we watch this, this is what it looks like. It's just like bouncing around. They're going to shoot one in. They're going to shoot one in, watch, and they'll like excite the system. This is PFC. It's masses and springs. If there's no damping, it's going to vibrate like this forever. If there is damping, it will eventually stop vibrating. I completely love this. The snap trap game is an example of a PFC model in reality, and this is an even better example of a PFC model in reality. Okay. This is this idea that you have a single particle vibrating. So therefore it's moving up, it's moving down, it's moving up, it's moving down, it's shaking back and forth. There you go. This is the period. Goes up, down, back. That's one period. Tn, that's seconds. And it turns out that for the type of integration we're doing, this is what the critical time step is. Tn over pi. And if you do Tn over pi, you get sample here, sample here, sample here. So this distance from here to here is what the time step. It has to be smaller than that. If you make it bigger than that, the system will blow up, meaning that suddenly your computation will just, instead of the new position being 2 millimeters, it'll be 2e to the 29 millimeters. It'll completely blow up. If you're smaller than the critical time step, everything's the same. Get the same answer all the time. And so what we want to do is we want to have a way of estimating this thing. Okay. And I'll just suffice it to say that for a given assembly of springs, we can do an eigenanalysis of that system, and we can completely theoretically calculate this guy that's vibrating the fastest. However, if we do that, it would take forever because it takes a long time to do an eigenanalysis. So instead, we do an estimation procedure to get an upper bound, and effectively, we take a particle and we come up with like an effective stiffness. So here's a simple system, a spring, a wall, and a particle. And if I excite this, it's going to go back and forth, and this is what its period is going to be. The period of this system is related to the mass and the stiffness. Notice, if I take this system and I make the mass bigger, it vibrates slower. This period gets bigger. If I make it stiffer, it vibrates faster. Right? If this is a bigger number, the period is smaller. The period is the width of this, so this thing gets compressed, so it vibrates faster. Okay? So this is an important thing because we're going to do an equivalence to this. And what we're going to do is we're going to say, here's a mass, here's a particle, and here's the contacts. And if you remember, every contact has to have a Kn and a Ks. Even for the complicated models, they still end up, in the end, having a Kn and a Ks. And so if we have this problem, here's a single mass point. It's got these 6 springs around it. That's what it is. We come up with a way of turning this into this, where we get an effective translational stiffness and an effective rotational stiffness. And if you want to look at the manual, you can find this. I love this thing. I derived this thing years ago. It's like a 20-page handwritten derivation, and the equation has, oh my God, it has like about 40 terms in it. And it's in the manual. And I'm sure no one ever has looked at it, but that's the basis. So for a mass, we can estimate then, notice critical time step. It's related to the square root of mass over stiffness. Mass over effective stiffness, right? So this is what we're going to do. We're going to go to every particle, figure out what these are, compute these 2 terms, and says that particle is vibrating this fast, so it needs a time step of 1e minus 3. But there might be one here that's vibrating even faster. So we go through all of them, and we take the smallest of all. And that's how we get the critical time step. Okay. And one of the results of this is that the system can change. If we take a collection of springs, a collection of PFC particles in a box under gravity, they form a pile. And now we put a wall on top and do an odometer test. We start squeezing it. When we start squeezing it, we get new contacts. So there used to be a particle in the middle that had 3 contacts. It had this much stiffness effectively. But now there's 4. Well, as soon as I add 4, I add more springs. So this guy is surrounded by a stiffer system. So therefore it's stiffer. This number is bigger. Time step gets smaller. And so that's an example where the stiffness is changing. Not the stiffness at each contact. The Kn and Ks are the same, but the effective stiffness that the mass feels, it's a function of how many there are. Okay. So this is why in a PFC system where you're squeezing things and new contacts are forming in things, the time step is going to slightly be changing as we go. Okay, ask me questions.
And how do we calculate the effective stiffness with all this?
Yeah, the effective stiffness is described in the manual, and I can show you where it is. And I'm so excited about it because I did the derivation. That's all I'll say.
Okay.
Okay. But it's in there, and I'm not going to talk about it. It would be it would be super fun for me, but maybe not for you.
Okay.
Okay. In fact, here's a good story. So I did this. This was when we were getting one early on in PFC, and there was giant pressure because Itasca's a business and we have to make money. And so we have to like get this thing done so people can pay us for it. I could care less about that. I just want to do research. And so we had to get this thing out, and it was behind schedule. And the guy who's managing it all is just like killing me. He's like, every week, come into the office. How come it's not done? And I'm like, I'm working out how to compute the critical time step. Oh, come on, that doesn't really matter. Just get something out there. I'm like, I'm sorry. I have to do this, and it has to be done right, or the code is just simply not going to work properly. So then I went and did this, and I wrote this enormous equation. And at the end, you go through all these steps, and then you list out the equation. It's like 3 pages. And then at the end, I put, whew. Like when you say, oh my God, I did a lot of work. Whew, I'm done. And I put that in there. It actually is in the equation. It says, whew, with an exclamation point. And back in those days, we had a person, and she was a typesetter. She took all the documents and turned them into the manual. And she didn't know anything about physics, and she didn't think very many things were funny. And so she took out the woo. She thought that was unprofessional. So, but I think it was fun. So, okay. Oh, again, this is what we just talked about again. The critical time step may change during a simulation, and this is my walking through what I said when you put balls in a box. Now let's talk about damping. Okay. Again, note in some of these, go ahead.
Sorry, before that, I have a question. So can we also track the critical time step as we do, for example, with the force chain, magnitude, and other stuff, or
Yes,
it doesn't matter?
You can if you want. You can track it, and you can take a history of it, and you can watch how it changes. It usually doesn't matter because as long as we're making it small enough, everything is happy and we get the same answer. And if it gets too big, nothing makes sense.
Okay.
But you can track it. You can track everything, PFC. Okay. Notice again, I haven't been pointing this out. There's always these little magic things here. And these are, again, pointing off the whole entire, they're either pointing off to sections of the manual or to those note sets of mine. So damping. As you know now, we are doing F equals ma. That's what I mean by the full dynamic equations of motion. And even if we have a quasi-static problem, like an odometer test, particles being squeezed by a piston, nothing really is happening in there. They're just being squeezed. There's a force, and we're slowly moving it, so the force is slowly growing. We call it a quasi-static problem. We still are solving F equals ma. And so think of those tennis balls with those springs that we saw. If that was a PFC bond, if we took those springs, forget about PFC, and if we squeeze them, when we start to push from the top, the whole entire system is going to be vibrating like that. Okay. And so that vibration can start to get really big if you don't have a mechanism for removing it. And so that's why we end up putting in damping, okay? And so what sort of damping do we have here? We have frictional sliding. We talked about this a little. At a contact, if there's a concept of a friction coefficient, when that thing is sliding, that energy is being lost, okay? But for most systems, that's not very much of a loss. And so we need other types of damping. And so there's two kinds of damping. We can put in dash pots at the contacts. A dash pot is like a shock absorber in a car. Your car has big springs that hold the body and connect it to the wheels. But when you hit a bump, the car goes up and down and it stops vibrating after a while because there's a dash pot. There's a shock absorber, we call it. That's what these things are going to do. We also have something called local damping. And that's going to actually, doesn't care about the contacts. It's going to actually apply a special external damping force to make the particles stop vibrating. So let's unpack this. This is talking about some issues about local damping and stuff. You can read that in a minute. You can read that on your own. Here's the idea of local damping. Don't look at the equations here. Just think of the idea. So I'm a particle, I'm a tennis ball, and I'm vibrating back and forth, okay? What I can do is, as I'm vibrating, there's always going to be some resultant force. That's like, say, I'm moving to the left, and I'm stretching the spring, so there's a resultant force going the other way, trying to make me stop moving that way. So what I can do is I can say, oh, there's an unbalanced force. Well, I'm going to go and opposite to that. I am going to put in an external force that is going to resist the unbalanced force. And so by doing this, I can effectively there might be one particle shaking up and down. And what I'm going to do is, as it's shaking, I'm going to constantly be pushing against it to make it go slower. Sometimes I'm pushing down, sometimes I'm pushing up. There might be another particle that's shaking horizontal. And over there, I'm going to be pushing it to the right and pushing it to the left. That's what we call it local damping. Every particle gets this external magic damping force that's going to slow it down and take energy out of the system. And this is controlled by a single parameter called the local damping coefficient. And we typically set that between 0 and 0.7. Okay. And for most systems that are experiencing quasi-static loading, like an odometer test or a triaxial test or something like that, this is the damping we're going to use. And we're going to use alpha equal 0.7. It's very heavily damped. And so again, think of it as those tennis balls with masses. If I was slowly squeezing it, they're vibrating back and forth. This is going to remove that high frequency vibration. And that's the kind of thing we're typically worrying about. Okay? That's all I'm going to say. We're typically going to use local damping. There's also, for certain cases, dash pots. Remember our rheological system, surface 1, surface 2. Now we're going to add on these dash pots. And so there's a normal dash pot and there can be a separate shear dash pot. So there's two more parameters. Critical damping ratio. And this is going to be appropriate if you're doing like forming a stable pile. You have particles, they're falling, and you want them to sort of lose energy as they bounce against each other. This would be more properly doing the physics of particles bouncing off of each other. Okay. And then the last thing is there are other damping things which I mentioned at the bottom here. Okay. Again, for all the work that you guys are doing, you're always concerned with quasi-static loading, and so you can always just use the local damping. And the only thing to remember about that is that every particle has its own local damping coefficient, and by default, it's 0. So you're always going to end up saying, oh, particle, the balls are going to have a damping coefficient of 0.7. So you have to actually give that command. Otherwise, there's no damping. By default, there's no damping. Okay. All right. Last thing. Too many equations on here. Forget. Look at this. Look at this sucker here. Okay. Here is. Well, forget about that. Let's talk about this. So we have PFC model, and we have particles that we create, and we turn on gravity, and they fall into a box. Okay. And there's damping. So they're going to fall, they're going to bounce around a while, and then eventually they're just going to sit there and they're going to be in static equilibrium. And so one of the ways of determining that is just to cycle for a huge number of cycles, and eventually you're going to see that all the velocities are incredibly small, like 1 × 12, because they're just vibrating at this super small value. It's important to know that the velocities will never exactly equal 0, because when we're using a computer, we're using finite precision mathematics. And so when you sum things up and you want them to sum to 0 for everything to balance, they're always going to be within what they call floating point precision, which is like 1 × 12 or so. So that's the velocities will be like bouncing back and forth at 1 × 12. Well, that's going to take a huge number of steps, and you don't want to have to look at the screen as you're running PFC models to figure out when to stop. So one way that we can do this is with a command. And what we essentially do is this. Look at this. Here's a particle. It has forces acting on it, as we know now. Okay. We go to this particle and we sum up the forces, and that's the total. We're going to call that the unbalanced force. That's the F equals ma. It's the sum of these. F equals ma. If this guy's in equilibrium, when we sum up these forces, they'll be exactly 0. And so F equals ma, 0 equals ma. Acceleration is 0. That's where we're at static equilibrium. But they're never going to perfectly equal 0. So what you're going to do is you're basically going to say, let's look at the unbalanced force on a particle, and let's just divide it by something so that the ratio gets to be small when we get near 0. Okay. And what we're going to divide it by here actually is going to be just the magnitude of these things. We're going to sum up these forces as a vector. That's what this is. And we'll take the magnitude of that vector, and we're going to divide it by just the sum of these lengths. The result is this thing called a average ratio, epsilon. And what we're going to do is we're going to say, I want you to continue to take cycles until this ratio is less than or equal to some limiting value. And so all that you're going to do is you're going to give one command, model solve ratio average 1e - 5. And then PFC is going to happily run and run and run until that's reached. Okay. And we're doing that at an average. So we're going to say, on average, that ratio, because there might be 10,000 particles, they all have their own ratio. If the average value of all that is less than a certain number, stop cycling. And we're going to find that for most systems, if we choose that to be 10 to the -5, 10 to the -4, in that range, it's going to be at equilibrium. Okay. So those are the components of the physics of PFC. Okay. Now the question is, you need to learn how we actually run PFC, right? So far, I've talked about the discrete element method, and there could be all kinds of different ways now people could put that into a program. And so now I'm going to talk about how to work with PFC, given that this is the basic idea. Okay, with me?
Yeah.
Okay. Just a second. Yeah, let's just look one more high level thing. This is a summary now. I'm trying to summarize in 2 slides everything, the basic idea, what you need to understand. Again, particles, 3 kinds of particles, and walls. These guys, particles and walls, interact at contacts, right? The particles are rigid. They don't change shape. The walls are also rigid. They don't change shape. You tell it the wall made of 3 facets and you give it a velocity and it doesn't change shape. We use a soft contact approach. They overlap and we have to update the force and moment at every contact, and that's from a contact model. Okay. And there's different types of contacts depending upon who are the guys. Is it a wall hitting a rigid block? Is it a wall hitting a ball? Okay. Usually you don't need to care about that, but sometimes you do. So I have such a model. What is it? Well, really what you got to do is, how do I build a model? How do I assign boundary conditions? How do I assign properties? And once I've done that, that's it. Now the thing just runs. F equals ma, right? So what can we do for the particles? Particles always have a velocity at any moment, okay? And so I can either give a boundary condition. I can say the velocity is free, meaning F equals ma is going to be used to update the velocity. So if I want the system to behave like a real system of particles, everybody's free. And I let F equals ma decide how they move, okay? Sometimes I might want to say, no, I want that particle to move at 2 meters per second in this direction. So then what I do is I fix the velocity, which means I tell it what velocity, and whatever that is going to remain fixed. It's never going to change. So if I have a particle here and there's a pile down here, I can say, I'm taking my finger. I'm going to make that thing move at 1 meter per second in this direction. I'm going to fix its velocity, and it's just going to keep moving. And these guys are going to build up forces and do whatever, because that's my boundary condition. Okay. So it's the velocity that I'm doing to give a boundary condition. I'm not like saying the displacement is 0. There is no concept of displacement in a discrete element model. Displacement is a concept of a small strain system. We have a reference configuration and we look at motion relative to that reference. That's what we think about as a displacement. In PFC, you're not doing that. You don't have a reference configuration. All that you have is at the current time, at the current state of the system, you have velocities everywhere. That's all you have. What else can you do? So a particle, you can make its velocity, you can fix it to remain the same, or you can let it be free. And notice there's 6 degrees of freedom. By that, I mean there's 3 translational components of the velocity, and there's 3 rotational components. So you could say the velocity in the y direction only is fixed. The other directions are free. If it's free, it does F equals ma. Okay. You can also have an applied force acting on the body or an applied moment. And so this is going to act at the centroid. So you can somehow say, okay, hey, this guy up on the top is being pushed with this much newtons, and that's an applied force, and that's always going to be acting on that body. So now when I sum up all the forces on the body to get F equals ma, I'm going to sum up the contact forces and your applied force. Okay. The other thing is that there can be body force. This is what we talk about of how gravity is done, right? You did this in physics as well when you learned about gravity. You say, oh, the mass of the body times the acceleration of gravity produces this magical thing we call a body force, which is what the body feels. So that's just naturally going to happen. If you turn on gravity, depending on the mass of the particle, there's going to be an externally applied body force acting on it. Okay. And that's it. There's nothing else you do. Particles. And with the walls, it's even simpler. The walls don't do F equals ma. Think about it. F equals ma. That means you got to have mass. Walls don't have mass. They're just surfaces. So the only thing is you just specify their velocity. It's always fixed. It always stays the same. You set it to 3 meters per second in this direction. There you go. As the model goes on, you can change it constantly, but you're the one telling it what to do, not F equals ma. Okay. And then the particles, think of it this way, like the particle, it has all these attributes, we call them. All this data associated with it. So I have one particle and it has a position, it has a velocity. If it's a sphere, it has a radius. It has tons of stuff. Those are called attributes. Velocity, position, density, for example, okay. Same thing with walls. When it comes to contact models, we call them a different thing. We call them properties. And so for this linear contact model, remember we had Kn, Ks, and friction coefficient. So we call those things properties. It's a subtle difference, but that we're going to use these two different terms in the world of PFC. So if we want to look at the velocity of a ball, we're going to give a command that's going to say ball attribute velocity, ball list attribute velocity. But if we want to look at the normal stiffness of a contact, we're going to say contact list and a property normal stiffness. And let's not worry about that other thing there. Okay. That is the end of the PFC physics thing. Okay. And I think what I want to do is stop now. Okay. And here's what we're going to do next time, next Monday, same time, same place. Now we're going to just actually work with the code. And we're going to go through a very simple problem and build the model and watch what it does. And in the process, these things will all get reinforced. And you'll get an idea of what it's like to run the code. Okay?
Okay.
So, thank you for your attention. And you can look forward to another picture of my garden a week from now, and we can see how much it's grown.
Okay.
And are there any final questions?
Yeah, I have a question. I just wonder why we need a critical value for the time step.
Ask your question again. What?
I just wonder why we need a critical value for the time step.
Because of this here. Okay, see this? This is the PFC model. And it starts vibrating. The masses, these guys start bouncing back and forth because they're surrounded by springs. Do you agree? They're moving, they're vibrating.
Yeah.
Okay, let's look at one. This is its position versus time. So it's moving up, it's moving down, it's moving up. So it's a sine wave. Okay.
Yeah.
This is the time it takes for it to move up and down and back where it was. This is the period. Okay.
Yeah, yeah.
Okay. Now, every single one of these is going to have a different period in general. Some are vibrating fast, some are vibrating slow. Okay.
Yeah.
The one that's the fastest vibration, that means that this time is the smallest. We have to keep updating the position of that thing. Okay. So we know its velocity right now at the beginning. There it is, velocity at time t. Now, notice the velocity is always an arrow that lies along this curve, right? The slope of this is displacement versus time, right? We have to, knowing the information here, we write the equations to compute the new velocity. That's v plus t plus delta t, right? And then knowing the information here, we compute the velocity here, and we keep doing that. Well, you have to, if this is the system, you need to sample it about 5 times over this time so that you can track this velocity. Because knowing all the derivatives, local information here, you cannot compute what it will be over here. You have to trace this. Sample, 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 sample. And so this is why there has to be a critical time step.
Yeah, that makes sense. I understand.
Okay. And if you go through here, this period is related to the mass and stiffness in the system. So we can estimate the fastest vibration. And if we estimate the fastest vibration, we can estimate a time step. So
Yeah. Yeah, I understand. Yeah, yeah.
okay, good. So I will send you the video of this, and I'll send you this whole set of the current state of the course. As you know, it's evolving every time I go. So every time you get one, just throw away the old one and just keep the latest one of the materials. And if you have any questions, just send me an email along the way here. And otherwise, I'll send out an invitation and we'll do this again next Monday, same time. Okay?
Okay.
Thank you all for your attention. I appreciate that you're taking this course. It's very helpful to me to make things better. Okay?
Thank you, Dr. Potyondy.